supposed to, all the way till the final exam. But between now and the final exam, the interruptions are quite a few. With Diwali and then Antaragni and the spirit of November and a new development, even the cultural festival of IIT Delhi is coming in the way. So all I can say is the choice is yours. So I was telling you that the previous lecture and the present, that is today's lecture, will involve a certain amount of vector calculus, and I will refer you to books on engineering mathematics for filling in the gap, in case you don't remember. Then as we move forward, we will try to work with the Cartesian form or cylindrical coordinates, polar coordinates version of the coordinate free form. This vector calculus involves the operator del, so derivative in vector form. Okay. So you might be familiar with dot products, and double dot products, cross products, inner products, outer products. So these are some terms that are used. So but we will go through the motions at a certain pace. You will have to fill in some gaps here and there, unless you remember everything. Okay, so again, in writing in coordinate free form, so remark, catch up on the mass balance equation. This is the incompressible form of mass balance equation. What is the momentum equation? It is just mass times acceleration is equal to sum of all external forces. External forces are body forces and surface forces. Now, we dropped the control volume. We said let control volume shrink to a continuum point. This is equivalent to saying we are doing calculations on a unit volume basis. So, it is mass times acceleration on unit volume basis, which is density times acceleration. Now, this stress quantity, stress is force per unit area, but force is a vector, area is a vector, that makes sigma depend on two directions. It has one magnitude and two directions. Symbolically expressed okay. So, because it depends on two directions, we sometimes add two tildes to it. So, this is a small fluid element. See, when you write x x, x y, it is a Cartesian form of sigma. So, in the momentum equation, it is in coordinate free form. So, if you pick your coordinate system to be polar coordinates, then you have to write sigma in polar coordinates, del in polar coordinates. What is u in polar coordinates? U in Cartesian coordinates? uv. What is del in Cartesian coordinates? And that is sigma in Cartesian coordinates. So, in the form of a schematic, this is sigma x x, which is the force acting on the x face. X face is the face to which x axis is normal, and the second subscript is the direction of the force itself. So, x x. This is sigma acting on the x face in the y direction. So, in this manner you can make other entries. This is sigma y y. This is sigma on the y face in the x direction. So, so, on the right face, the stresses are shown in the positive direction just by convention. So, you can fill up the rest. So, we were talking about some limiting cases. So, one limiting case is fluid statics. So, when you talk of water, then it becomes hydrostatics. So, in fluid statics, the stresses have to reduce to pressure with a negative sign, okay, because by convention pressure is taken to be compressive, and we also have the result that under static conditions the magnitude of pressure remains the same irrespective of the direction of the plane, which is Pascal's law, which tells you that sigma x x, sigma y y should all be equal to minus p. Symbolically, so this sigma can be written as sigma I j. So, this u may be written as u I. Okay. So, this del, if you read books, may be written as del comma I. Okay. This comma indicates partial differentiation. I is with respect to the direction. So, I will have indices 1 and 2, 1 is x, 2 is y, and 3 is z. So, in fluid statics, the limiting case sigma I is equal to minus p. So, minus p. So, is more commonly written as sigma I j equal to minus P delta I j, which gives you the specific result that shear stresses, that means when I is not equal to j, sigma x y, sigma y x, shear stresses are absent. So, the equation for hydrostatics is sigma I j equal to minus P delta I j. So, that you can substitute in the momentum equation, u is 0. So, you will have a balance between pressure and body forces, which is the equation of hydrostatics. The second simple flow field we have studied is Newton's parallel plate experiment. Where we wrote F by A equal to mu u over h. So, if you consider a small element, so now we are specializing Newton's parallel plate experiment all the way to the element level. So, then this is sigma y x. So, this is the fluid element. So, you can associate F by A with sigma y x. So, this element will undergo shear deformation. This is getting deformed because of the movement of the plate. So, if you think of, this is at the elemental level, if you think of a small interval of time delta t, then let us say a point such as A will move to a point such as A prime. How much is that movement? It is some velocity times delta t, that is the distance. And how much is the shear deformation? That is the angle through which that edge has moved. We are talking about small increments in time. So, the angle is also small. So, that angle can be estimated as opposite side over adjacent side, which is u delta t divided by the height of the element, okay, which is delta y, right, it is a small element. So, this angle, if you call it delta, delta is equal to u delta t over delta y. Relative, now this u delta y, delta, this is what is that u? U is the relative velocity between the top surface and the lower surface. Right? In Newton's parallel plate experiment, the lower surface is fixed, but in general, if you think of a fluid element within, it is the relative movement of the top surface with respect to the lower surface, and delta dot is obtained by dividing by time. So, this really becomes this derivative. So, sigma y x is equal to mu times the derivative of velocity. So, in the simple, so this is the stress strain rate relationship in the Newton's parallel plate experiment. These are some limiting cases we have studied earlier. So, what do you do with this formulation? What is the goal of the subject as we see it? Goal has always been to find forces. So, now in the new approach, we find forces from stresses. stresses are to be found from velocity and pressure. So, let us say calculation of forces. Let us take an example of flow over a flat plate. So, you may consider a fluid element like this. This is a fluid element adjacent to the flat plate. So, the lower edge of the element is in contact with the flat plate. So, on this surface it is sigma y y and we showed sigma y x. So, on the plate we have sigma y y and sigma y x. Okay, these are the stress components acting on the plate at a point. So, this should not come as a surprise because we are doing local analysis. So, locally the force will be the stress component multiplied by a local area. Now, these quantities sigma, velocity is changing everywhere, sigma will also change everywhere, pressure is changing everywhere. So, at a point you have a force contribution which you have to integrate over the surface and get the total force. Now, let us okay, so let us write the force acting on the surface in the x direction. Okay. This is the force. Now, we are doing a calculation of force on the surface. So, I will just write it once. Force acting on the surface in the x direction. You remember that the control volume analysis was for the fluid medium, and then we got forces acting on the fluid medium, and then we transferred that force information onto the solid surface. We are doing the same force calculation now with respect to locally available flow properties, these properties. So, this stress tensor was for the fluid element, and now we are transferring the data sigma y y, sigma y x onto the surface. So, this is on a small element that is centered on point P, and this we have to add up over the entire surface. Since force is a vector, the addition has to be vectorial, which means component wise. So, what is capital X? It is simply integral 0 to L sigma y x dx, where sigma y x is to be evaluated at y equal to 0. Similarly, capital Y is equal to integral 0 to L sigma y y at y equal to 0 dx. So, these integrals will give you the forces acting on the surface. So, now it remains to find sigma. Now, Newton's parallel plate experiment gives us a hint that you can find sigma in terms of velocity. So, now let me comment on boundary conditions, that whatever be the velocity field elsewhere away from the surface, at the fluid solid interface, this surface does not allow flow to pass through. So, the normal velocity is 0. So, we are talking about a solid interface where the solid is stationary. So, V is 0 and the second condition is often called the no slip condition. That means, the fluid will not slip over the surface, the fluid. So, water flowing on this surface is stationary. So, the water particles that are connected to the solid surface will also be stationary, and there is fluid movement above, creating a velocity variation. Okay. So, you did some examples earlier where you saw a velocity variation. Away from the surface there was some flow, at the wall velocity came down to 0, which is the wall velocity. If the wall is given some motion like in Newton's parallel plate experiment, then the fluid particles are also dragged with the surface. So, there is no slip between them. Fluid velocity is equal to solid surface velocity. That is called a no slip condition, which are by and large observed in the type of applications we have dealt with. So, if u and v are 0, fluid is stationary. So, in that case the normal stress components will reduce to pressure. Okay. So, sigma x x, that you know from the previous example. So, capital X rather I am sorry, not capital y. Let us write y is equal to 0 to L with the negative sign p at y equal to 0 dx. Okay. So, we have a further simplification for capital Y. What about capital X? So, we are talking about the near wall region. So, at the wall it is 0 velocity, and let us say you have a velocity variation like this, but close to the wall in this region it looks like Newton's parallel plate experiment. You do not have a plate, but you have fluid, that wall is fixed, and then fluid layers are flowing over the surface. So, it looks like Newton's parallel plate experiment. So, in that case sigma y x, so here sigma y x, which is at y equal to 0. What is this is y, this is x, is mu y equal to 0. So, capital X can be written as 0 to L dx. So, if you know the velocity distribution, you can substitute here and find capital X if you know the wall pressure. So, the stress at the wall is called wall stress. So, if it is shear stress, it is wall shear stress. Pressure at the wall is also called wall pressure. So, wall properties. Okay. So, this is our overall approach to finding forces on the object. So, if you have velocity distribution, find the stress distribution and integrate stresses suitably to find forces on the object. This is the local to global approach. So, let us look at an example in polar coordinates. So, polar coordinates are r and theta. Let us say we are studying flow past a circular cylinder. Okay, so this is a part of a cylinder and this is a small element, this part. What is the length of that element? It is r d theta. Okay. So, you can construct a fluid element in r theta coordinates and show stress components sigma r r, sigma r theta. Sigma r theta is the stress component on the r phase in the theta direction. So, it is a shear stress. Now, you will have another sigma r theta on the inner side. So, after all you want to find forces. So, these are these crosses indicate the surfaces that are going to be in contact. One is from the fluid side and one is from the solid side. So, if I just look at the solid surface, then it will have sigma r r, sigma r theta. These are the polar components of stresses acting on the solid surface at a point defined by angle theta. And what is the radial coordinate at that point? It is r equal to capital R, the surface of the cylinder. So, we are trying to calculate forces acting on the cylinder in terms of the local stresses in polar coordinates. So, now I want to find force acting on the cylinder in the x direction. So, this x direction is also the flow direction. So, under those conditions, force acting on the cylinder in the flow direction is called drag and sometimes given a symbol d. So, you have you remember drag coefficient for a circular cylinder. Okay. You also remember drag coefficient for a sphere. You already have it in the form of handbook data. So, now we are talking about calculation of those drag coefficients from the local description of the flow field. How will I get the local description of the flow field? That is by solving the local form of the mass and momentum equations. Those equations look somewhat complicated. So, we will deal with them as we go along, but for the time being let us say you know stresses, then this is a small element whose length is r d theta. So, you have to find the force acting on the entire surface by integrating sigma r r and sigma r theta. So, you will notice that sigma r r has an x component, sigma r theta also has an x component. Okay. Sigma r r will be cos theta. So, this is x is equal to integral, the variable is theta, which is 0 to 2 pi, sigma r r cos theta minus sigma r theta sin theta r d theta. R d theta is the elemental length, and similarly capital Y, which is the force acting on the cylinder in the y direction, and the force acting on the cylinder normal to the flow direction. What is this flow direction? When we say flow direction, we always refer to the upstream, because near the object it is all disturbed. You do not know if the fluid medium is going this way or that way, but we refer to undisturbed conditions. Overall flow is coming this way, and the force acting on the object normal to the inlet or inflow condition. If it is normal, it is called lift. In the flow direction, it is drag. So, for this example, capital Y also coincides with lift. And just by looking at this picture, you can see that the two of them will add up. where these stresses have to be evaluated at r equal to capital R. Like the flat plate problem where y is 0, here it is r equal to capital R. Now, sigma r r at r equal to capital R is equal to minus p, which is evaluated at r equal to capital R and is a function of theta. And sigma r theta will be mu times the derivative of the theta component of velocity. So, this is from the flat plate experiment. You have to look at the tangential component of velocity. So, these are the polar components of velocity. U and v are in x and y coordinates, u are u theta in r and theta coordinates. So, these are all 2D versions, 2-dimensional versions. Now, even though we have not done numerical calculations, you can quickly anticipate some results. For example, the shear stresses are multiplied by viscosity mu. Now, if you think of air versus water, water versus oil, let us say between air and water, viscosity from your gut feeling, from your past knowledge, you know viscosity of air is much smaller than viscosity of water. So, you know that in air the shear stresses are going to be small. So, you are going to carry out a calculation, I say its flow past a cylinder in a wind tunnel. So, you may approximate viscosity to be 0 for air, but if it is water tunnel, viscosity will be significant. If it is oil, viscosity will be very, very high. So, it is not that these are only algebraic expressions, but they also carry a certain amount of message which can help you carry out calculations. So, let us go back to a relationship between stress strain rate relationship. So, here you have to refer to the comment I made last time, that in our global analysis we used handbook data that was device specific. Was it flow through a tube, flow in a pump, or flow past an object? So, that was device specific, but when you go to the local scale, you do not see the device is outside. So, what you see is the material. So, you replace the device characteristics by material characteristics. So, the stress strain rate relationship is a material behavior function. And we have been studying material behavior in the framework of Newton's parallel plate experiment again, and we have been talking of a Newtonian fluid. So, if you remember the discussion we had, we wrote something like this relationship was taken to be linear with a slope equal to viscosity. Which viscosity? Dynamic. When we say viscosity, we mean dynamic viscosity. There is one more viscosity which is mu over rho, called kinematic viscosity, nu. But when we say viscosity, it is dynamic viscosity. So, a Newtonian fluid is one for which there is a well defined viscosity independent of the strain rate. Del u del y is the strain rate. We just saw that in the previous slide. So, that expression was for a parallel plate experiment, but we would like to generalize. Okay, so, we constructed sigma as sigma epsilon I j, and the strain rate is given a symbol epsilon, okay, and this dot indicates time derivative. The rate of this is epsilon is strain, epsilon dot is strain rate. Now, you might remember from your previous courses, let us say you may remember elongational strain. So, what is elongational strain? You take a small element of the material and pull it, and then its length changes from L to L plus delta L. So, the delta L divided by original length is the elongational strain of that element, and then it is connected to the stresses you have applied. Higher the stress, greater is the elongation. For commonly used materials like mild steel, for example, it is a linear relationship between stress and strain, but in a fluid medium you apply stress and the material flows. So, the response is seen as strain rate. Okay. So, the rate at which the elongation keeps increasing is a measure of the stress applied. Now, in the context of local analysis, you consider an element A B whose length is delta x, it is a small length. So, after some time is a very small increment in time, this point A has moved to A prime and B has moved to B prime. I am just talking of a 1D context. So, A has moved through a distance, let us say psi, then B is a neighboring point, it would have moved through a distance which is given by Taylor series approximation. So, if you know the properties at one point, you can get the neighborhood properties through Taylor series expansion, which is an infinite series. It is now truncated after the first term. Why? Because delta x is small. The other term would be delta x square, which is very small. So, the elongation of the element A B is this partial derivative del psi del x delta x, and the elongational strain will be this extra term divided by delta x, which is del psi del x. And if you want to get the elongational strain rate, you have to differentiate with respect to time. Now, here we are talking about fields that are continuous in space and time. So, you can interchange the order of differentiation. So, if you differentiate del psi, what is psi? It is the displacement of point A. Okay. So, the original distance between A and B is delta x. The new distance between A and B is A prime B prime is psi plus del psi del x delta x. So, divide by delta x, because that is the definition of elongational strain. and the strain rate is obtained by differentiating del psi del x with time. Interchange time and x, that means you differentiate psi with time, which is, how much is that? Derivative of psi with time is the x component of velocity, right. So, this is simply del u del x. Okay. So, you can see that strain will be in terms of displacements and strain rates will be in terms of velocities, and then we are looking for a generic relationship between strain rate and stress, which we plan to put in the momentum equation. Okay, so, this is in the 1D context. In general, we have a 3D element, that was a 1D element, but then let us do the calculations in 2D. This is the xy plane, and let us say this is the initial element. So, we are going to carry out a similar analysis. Instead of A B, now we have an element, a rectangular element A B C D. This is what are the dimensions of A B C D? Delta x, delta y, and this element is moving in the flow field. Okay, and we think of the position of this element after the passage of some small time increment delta t. It is going to deform. Why is it going to deform? Because there is a stress field around. So, after some time, this point A, now this has become point A prime through a displacement psi in the x direction and a displacement eta in the y direction. So, let us say so these are points B prime, C prime, D prime. Of course, if the fluid is incompressible, then the two areas will match, but the element will still undergo deformation. Okay. But this is an exaggerated kind of a view. So, let us draw the element. This is A B C D. This is the original element which is now deformed. So, this was the position of B. What is the position of B prime, which is, we have just found that out, this del psi del x delta x, okay, which after differentiation. So, this is psi x delta x. Similarly, this distance is eta y delta y, and the corresponding strain will be divided by delta y, and then time derivative will give you the y component of velocity differentiated with y. Okay. So, what are these strain components? So, earlier this was just epsilon dot, this was epsilon equal to del psi del x, and this is epsilon dot. But in the 2D setting, you have strain of an element in a given direction. So, strain of the x edge, this A B is the x edge in the x direction. So, we call it epsilon x x. Then we have the strain of A D in the y direction, that is epsilon y y. So, we have expressions for okay. So, this is derivative of v with respect to y. How did we get it? it is this eta y delta y divided by delta y time derivative. But we also have the deformation of the fluid element. So, this is, you can see it is a generalization of Newton's parallel plate experiment. In Newton's parallel plate experiment, you had one plate moving with respect to another, just we forced it to go that way. But in a general field, the element can deform in 3D, but this is a 2D projection of it. So, you have two deformations. You can see an angle here delta 1 and you can see another angle here delta 2. So, let us write delta 1. How much is delta 1? It is the opposite side, that is the movement of point B prime in the vertical direction. Okay. So, we had psi x delta x as the movement of point B prime in the x direction. So, it is also moving in the y direction, okay, divided by the original length, which is, that is the this is opposite side over adjacent side. That will give you an estimate of delta 1. Okay. It should be tan, but we are talking about small angles, small time increments. So, tan delta is delta. So, this will be that means the movement in the y direction. So, this is eta x delta x over delta x, and delta 1 dot is equal to V x. Similarly, delta 2 will be u y. I am just reminding you that the suffix indicates partial differentiation. So, these are delta 1, delta 2. Now, for an element that is undergoing deformation in all dimensions, it is common to define its average deformation as delta 1 plus delta 2 divided by 2, which is the average deformation. In 3D, it will be delta 1 plus delta 2 plus delta 3 divided by 3, and the average deformation rate will be delta 1 dot plus delta 2 dot. So, if you have epsilon x x, epsilon y y, then the deformation rate would be epsilon x y or epsilon y x, but when you do the averaging, these two become equal. Is epsilon dot x y, which is epsilon dot y x, is equal to half delta 1 dot plus delta 2 dot, which is half u y plus v x. And let me write the other results also for comparison. So, just going from component level to a tensor level, epsilon dot I j will be, we have elements u x, v y, and then this half u y plus v x, it is also here. Okay. So, this is the strain rate in 2 dimensions. So, just an extension of 1D from elongational strain to elongational strain in 2 directions to shear strain or deformational strain that is possible in 2 dimensions. So, this is the construction of epsilon dot I j, and we are looking for a linear relationship between sigma ij and epsilon dot ij. Why linear? Because we are using a framework of a Newtonian fluid. So, generalizing Newton's observations that the stress strain rate relationship is linear. That is what he observed. So, that is being now written out in a multi-dimensional context. So, I will leave it as an exercise. If you are interested, you can show that the expression for epsilon dot ij in coordinate free form is del u plus del u transpose. So, we are out of time. So, on Monday we will talk about the stress strain rate relationship for a Newtonian fluid. Okay. That will then connect stresses to the flow field.